Okay, welcome back. Today we're going to continue Chapter 2, Linear and Quadratic Functions, taking a look at 2.3 with quadratic functions. Now, a quadratic function is a second-degree polynomial. So the typical form is ax squared plus bx plus c. A, b, and c are real numbers, and the domain would be all real numbers. Any value of x would be allowed to be an input here. The graph of a quadratic function is going to be a parabola. A parabola has a vertex, which is the minimum point should it open upwards, or the maximum point should it open downwards, and it increases off in either direction. Unlike an absolute value function, which meets in a point, the parabola is continuous and smooth. There's no sharp turns, no sharp corners. It is a smooth curve. Now, there's a couple of different ways that I can write the form of a parabola. We've got our general form, ax squared plus bx plus c. This is fine and dandy, and it's usually easy to work with the general form, but it's not very easy to graph. It's not very easy to do a lot of calculations with. The vertex, for example, has a form of negative b over 2a, and then I'll have to plug that in. This is a lot of work to find the vertex, and then I might not be able to tell where the parabola is going. So instead, what we would like to do is we would like to take a look at standard form. This gives me f of x is equal to a times x minus h squared plus k. And the reason we like to use standard form is that standard form looks like a transformation. It's got a shift to the right h and up k, which means that I can very easily track where the vertex is going, and a will represent a stretch or a shrink, depending on whether it's positive or negative. Notice that this a is multiplied by the x minus h, so a large a would indicate a horizontal shrink, whereas a smaller a would represent a stretch. Now, if you're given an equation in general form, usually your best bet is to convert it into standard form and then graph. This will usually be very nice in order to get a graph and easier than going through another method. Let's go through a couple of examples here. Let's suppose that I wanted to graph this equation, y equals negative 2 times x minus 1 squared plus 3. In order to graph this, I will treat it like a transformation. So just like before, I've got a shift right by 1 and up 3. This 2 represents a horizontal shrink, and the negative sign represents a vertical, this 2 is a vertical stretch, not a horizontal shrink. It's a vertical stretch because it is multiplied by the entire parentheses. If this was the 2 inside, so it was, say, 2x minus 1 all squared, that would be a horizontal shrink. But the fact that the 2 is outside the parentheses means that it's a vertical stretch. The negative represents a vertical reflection. And again, it's the fact that this 2 is outside of the parentheses, not directly with the x, but outside, indicates the fact that it's vertical. So I'll take this parabola. The vertex is equivalent to the shift here, so that means I'll have 1, 3. It's going to be a downward facing parabola. I know this because I've got the negative out front representing a vertical reflection. And it's stretched out a little bit vertically. So we can go ahead and trace. If we want to make this nicely to scale, we can plug in a couple of points other than the vertex and get a nice to scale parabola. But for the most part, when we want just a sketch, it's good enough to make sure we have the vertex correct and labeled, and that we have the parabola opening in the correct direction, and that we're able to identify whether we have a stretch or a shrink. Now, if I'm given a parabola that's not in this form, what I would like to do is I would like to complete the square. Let's real quick do a review of completing the square. The idea of completing the square stems to the idea that if I begin with x minus a, or let's say x plus a squared, then foiling this out will give me x squared plus 2ax plus a squared. What I would like to be able to do is reverse the process if I was given x squared plus bx. Notice that this b lines up here with the 2a, and I would like to figure out what I need to add in order to complete the square. Well, if b is equal to 2a, then that means a is equal to b over 2, and a squared is equal to b over 2 squared. So that's what I need to add to the box, b over 2 squared. So to complete the square, you'll write it out so that I have x squared. You'll add b over 2 squared after identifying what b is, and then you'll add that. Now, you'll need to add and subtract it so that you're not changing the equation. Let's go through this in an example here. So the first thing I'm going to do is I'm going to rewrite this in standard form, or I should say general form here. Negative x squared minus x plus 6. I don't like the fact that there's this negative here. It's making it more complicated for me. So the first thing I'm going to do is factor out a minus 1 from each piece. This will make it more straightforward to complete the square. Next, I'll look at this part here. X squared plus x. I could write this, if I would like, as x squared plus 1x. This 1 is my b, which means that b over 2 squared is going to be 1/2 squared, or 1/4. So I will need to get a 1/4 in order to factor this piece. Now, if I'm going to add a quarter, I need to also subtract a quarter, and the minus 6 will still remain. What that leaves me with is a negative x plus 1/2 squared minus, looks like what I'm left with is 6.25. I could also write this as an improper fraction of 25 over 4. That would be fine as well. Finally, I don't like the fact that this negative is outside anymore. It was good for completing the square, but now I'd like to put this in standard form, which means I should distribute the negative. Negative x plus 1/2 squared plus 6.25. And now I can tell what's going on here. I've got myself a shift left 1/2 and up 6.25. And I've got a vertical reflection. Putting all of this together, the vertex is going to be negative 1/2 6.25. And it's a downward facing parabola. There wasn't a stretch or a shrink, so it'll be a fairly standard looking parabola. Now, what we can do is we can complete the square with a parabola that's a very generic parabola in general form. Let's begin with y equals ax squared plus bx plus c all equal to 0. If I wanted to solve this equation without knowing what a, b, and c is, I can go ahead and isolate x. The first thing I'm going to do is I'm going to divide by a. X squared plus b over a x plus c over a is equal to 0. Next, I'm going to complete the square. What that will give me is x squared plus b over a plus b over 2a squared minus b over 2a squared plus c over a. This first part now is a completed square, so I will have x plus b over 2a squared minus, and I can complete this next part. So I can make this a b squared over 4a squared for this first piece. And for the second piece, if I want to get the same denominator, I will need to multiply the top and the bottom by 4a. So I will multiply here times 4a on the top and the bottom. And so what that will give me is it will give me negative b squared plus 4ac over 4a squared equal to 0. You may start to see where this is going, but if not, let's keep moving forward. From here, I'm going to isolate the part on the left with x so that I can take a square root. X plus b over 2a squared is going to be equal to, this should be a plus here because I brought the negative in over here, so I don't need to have the plus 2 times. That means that this will be equal to b squared minus 4ac over 4a squared. I'll then take the square root of both sides. This will leave me with x plus b over 2a is equal to, I'm going to have a plus or minus because I took a square root, b squared minus 4ac over 2a. Finally, I'll need to subtract this b over 2a from both sides, and I will get x is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. And you may recognize this piece right here as the quadratic formula. And notice what we began with. Ax squared plus bx plus c is equal to 0. By completing the square, we obtained what may be a familiar formula, a way that we can solve for x when I've got a quadratic expression equal to 0. Now, there's one important piece we're going to look at within this, which is the part under the square root. Notice that for square roots, we've been through this before, we know that we are going to be taking a square root, and I can either get 2 solutions or 1 solution, or potentially even 0 solutions. So let's take a look at the different possibilities. If the part under the square root, b squared minus 4ac, which we're going to call the discriminant, is positive, then I will get 2 unique real solutions. If it is equal to 0, then I'll get exactly 1 solution, because plus or minus, if the answer is 0, doesn't make a difference. They're both the same. If it's negative, then I will get exactly 0 real solutions. I'll have 2 complex solutions involving imaginary numbers, but we won't pay attention to those for a little bit. We're mostly concerning ourselves with real numbers for the moment. Now, that's all we've got for quadratic equations. See you guys next time.